Now, to answer to this $1,000,000 question that whether or not Java follows the ASCII encoding format, we have to go back in history and understand bit more about the character encoding formats, especially about the problems associated with the ASCII encoding format. Sir, are you trying to tell us that the ASCII format had some limitations associated with it? Certainly, yes. And the major problem with the ASCII format was that it supported binary representations only and only for English based symbols. That means the symbols of non English based languages were not included in the ASCII format. And it is quite evident to all of us as well. Just before some time, I had displayed the ASCII table onto the screen. Did any of my learners happen to find the alphabets of the Hindi language included in the ASCII format? Did you happen to come across the symbols of Kannada language, Malayalam, Gujarati, Marathi languages included in the ASCII format? Definitely not. Or by any chance, did you happen to find the characters of the Chinese language called Mandarin, which happens to be the most spoken language on the planet Earth, included in the ASCII format? Definitely no. That means clearly your ASCII format was biased towards the English language. It had left quite a lot of symbols of non-English based languages unrepresented, for which binary representations were not provided in the ASCII format. That is when one of the computer scientists proposed that look, we would continue to use the existing 128 symbols of the ASCII format as it is because we need them. But at the same time, we are also aware of the fact that to provide the binary sequences to those 128 symbols, only 7 bits are going to be enough. But however, since already in the memory 8 bits are going to be allocated, why don't we make use of that one extra unused bit and represent more symbols is what he had to propose. That means now if we would go ahead and try to include that one extra unused bit as well, in that case, can you please tell me in total how many bits are available for us to assign binary sequences? Absolutely correct. This time we have got 8 bits. And please think and answer to this question. Using a 8 bits long binary code, in total, how many symbols do you think can be represented? We have seen similar calculations previously, hence you should be able to answer to this question. Previously, we had the number of symbols and I had asked you to express it as power of 2, and whatever would be there in the exponent, it would simply indicate the length of the binary code. But in this scenario, we are already aware of the length of the binary code. It is a 8 bits long binary code. All that I'm asking here is how many symbols in total can be represented. Basically, it is a simple reverse engineering process that we need to apply here, which is if you have got 8 bits in total, how many symbols can be represented, sir? All that you need to do is raise that number 8 as the power of 2. Those many symbols can be represented. That means a total of 2 to the power of 8 symbols can be represented using a 8-bit long binary code. In other words, 2 to the power of 8 is nothing but 256 symbols in total can be provided binary sequences by just ensuring that one extra unused bit is put to use, which was anyways being allocated memory on the RAM. At the same time, I don't want my learners to assume that these computer scientists were trying to reinvent the wheel by trying to redefine all of these 256 symbols once again from scratch, because that was not the case. In other words, the existing 128 symbols of the ASCII format were carried forward as it is. Additionally, another set of 100 and 128 symbols were added to it. This combination is what was technically referred to as the ASCII extensions. Basically, these are the extended versions of the ASCII format. Great, sir. With these ASCII extensions, the ASCII format has been able to overcome its limitations of not representing the symbols of non-English based languages, because now we see that ASCII has evolved in such a manner. It has included additional 128 symbols. If this is what all of you are also thinking, I would simply say sometimes celebrating too early before the victory is quite a problematic thing. You never know what happens on the last ball. What do you mean to say, sir? All of you would be shocked to know what those additional 128 symbols were. I don't know how many of you have noticed it, especially whenever you're typing a message in your mobile phones. If you happen to long press on a particular key, you will immediately notice that there are different variants of the same character that are being displayed to us. For example, if you long press on the alphabet A, there are different variants. There is a A on top of which where there is a tilde symbol placed. There is a A on top of which there is a caret symbol placed. There is a A with two dots that are placed on top of it. Similarly, if you happen to long press on the character E, once again there are different variants of the same alphabet that are being displayed to us. And those variants, my friends, are nothing but the symbols of the Latin English language. I'm sure all of you have seen the Latin English alphabets. Anyways, this ASCII extension, which included the original 128 symbols of the ASCII format, along with that additional 128 symbols of the Latin English language, is what we technically refer to as the ISO Latin 1 ASCII extension. That means, to conclude, clearly neither the original ASCII format nor these ASCII extensions are going to extend the support to provide the binary representations for the symbols of non-English based languages. Both of these formats, let it be the original ASCII format as well as the ASCII extensions, to a certain extent support the symbols of only English based languages. That means the limitations of the ASCII format has not been overcome by any of these two formats. And not just that, things don't stop here. To make things even more worse, there were many attempts made to create encoding formats to support their local languages. Just because these Americans created a format called as ASCII which supported only English based symbols. But you know back then how the rivalry was between those two superpowers. Of course, they were not called as America and Russia back then. They were called as USA and USSR. And now just because Americans have done it, Russians also wanted to create their own encoding format. And they did go ahead and create an encoding format to support these symbols of the Russian language. And what did they name it as, sir? Since Americans named their format as ASCII, Russians named their format as Risky. And then we have this country called as China, which simply wants to gain monopoly over everything. Hence, it went ahead and created an encoding format that supported the symbols of the Chinese language. And what was it called as, sir? You can guess it, Chisky. But what about us, sir? You know how we Indians are. We would always maintain a very neutral stance, non-alignment movement, neither USA nor USSR. But then, since India happens to be the land of hundreds and hundreds of languages, we went ahead and created our own encoding format called as ISCI. And finally, we had a country by the name Vietnam, and it also wanted to create its own encoding format. And can you guess what did they name their format as? Not the whiskey that all of you are thinking of. Absolutely correct. They have named it as whiskey. Anyways, all the fun apart, I don't know how many of you are able to understand the point that I'm trying to convey here. The problem with these encoding formats which are local to their demographic regions, if I happen to type a message in one country and if I transfer it to another country, 100% the message might not be interpreted the way I had sent it. In simple words, the major problem with all of these encoding formats coming into the picture happens to be there was a lack of standardization. And not to mention, it was not just these countries. There were many software companies, they were creating their own encoding formats for their own software projects. Now, in order to standardize encoding and decoding of messages by the computers, in the late 1980s, there was a computer scientist by the name Joe Becker, the hero of this entire story. He was working for a software company called as Xerox. And like I had mentioned, just like those countries, there were also few software companies who had created their own character encoding formats that would be used in the software projects that these companies would be developing. One such company was Xerox. It had created its own character encoding format called as Xerox Character Code Standard, in short XCCS. Also, let me tell you a bit more about this computer scientist Joe Becker. He was quite a specialist in character encoding because of the vast experience that he had gained by working on the XCCS format for quite a long time. And he finally, one fine day, had decided to own up the responsibility to solve the problem of standardization across different character encoding formats. And he knew the only possible solution would be to create a single character set, a universal character set that would include the symbols of most of the languages across the globe, which he eventually named it as Unicode, with the intent to convey that it is unique, it is unified, and provides a universal encoding. When he and his friends started accumulating the symbols of different languages around the world, he had initially assumed that only 16 bits should be more than enough for this purpose, because he knew using 8 bits only a maximum of 256 symbols can be represented. But now that he knew that he had the responsibility of including all these symbols of most of the commonly spoken languages across the globe, which would definitely be more than 256 symbols, for which 16 bits would be sufficient. With this intent, finally, in the year 1991, a group was formed. The job of this group was to regulate the formations of the Unicode standard. And this group included some of the prominent software corporations as its members, such as Apple, Facebook, Microsoft, Google, IBM, Netflix, and many more. And this group was officially called as the Unicode Consortium. Just like how the ASCII format had a governing body called as ANSI, everything about it I have already spoken. 1960s, 128 symbols, 7-bit binary code. Similarly, Unicode Consortium happens to be the governing body for the Unicode standard. And under the Unicode Consortium, in the very same year 1991, the very first version of the Unicode standard was officially released. And you will be shocked to know as to in total how many symbols were represented by the very first version of the Unicode format. A total of 7,129 symbols were represented by the very first version of the Unicode standard, and this was way back in 1991. I hope all of you are able to notice as to what a huge leap it is, from 128 symbols to 256, and now from 256 directly it is 7,129 symbols. And please embrace yourself for an even much bigger shock, which is in the latest version of the Unicode standard, which happens to be 15.1, that was released in the year 2023. A total of around 1,50,000 symbols are currently supported in the Unicode standard, for which binary representations have been provided. Definitely, now we can conclude that the Unicode character encoding format happens to be quite a fair character encoding format that is not biased towards a specific language. It is going to represent symbols of thousands and thousands of languages. Now, this is all about the character encoding formats. Speaking of the language Java, that was also invented in the same decade of 1990s. The creators of Java were now in a state of ambiguity as they had to choose either between the ASCII format or the Unicode encoding format. But however, since Java happens to be a platform independent programming language, also an aspiring internet programming language, naturally the founding members of Java had the responsibility to ensure that their language extends the support to all of the languages spoken over the internet. Hence, for this reason, the inventors of Java had to take this tough call and make a wise and an intellectual decision that Java does not follow the ASCII format. In fact, Java follows a character encoding format called as the Unicode format. This is the answer to the question that has triggered this entire discussion, that whether Java really follows the ASCII format or some other character encoding format. The straightforward answer is Java follows the Unicode character encoding format. Hence, if you happen to come across any of the modern day web applications, and if you notice it supports a wide range of languages, it is quite clear that those applications have not been developed using any of the programming languages that abide by the ASCII encoding format. Undoubtedly, I can guarantee on this, they have been developed using such programming languages that definitely follow the Unicode format. Perfect, Zabi sir. We have now been able to understand that the char data type in Java does not follow the ASCII format. In fact, it follows the Unicode format for all of the reasons that you have just now explained to us. But then, what about the size of the char data type in Java? What if within our Java program, we happen to declare a variable using the char data type? Then for that particular variable, in the RAM, in total, how many bits would be allocated? To answer to your question, I would like to reiterate one of the statements that I had previously made while introducing Joe Becker and the Unicode standard, which is Joe Becker had initially assumed that only and only 16 bits would be more than enough to include the symbols of all of the commonly spoken languages across the globe. And the rationale behind this ideology was the Unicode standard had primarily aimed at including the symbols of only and only modern day languages. They were least interested in the symbols of the ancient languages. And where did they find the symbols of modern day languages, sir? Basically, the symbols that were found in all of the newspapers and magazines printed in the world back in that time. And when collected, collectively, the number of symbols turned out to be in the modern languages quite less than 2 to the power of 14, which is nothing but 16,384. Of course, in the latest version of the Unicode standard, we have got 1,49,000 change symbols. But out of them, less than 16,384 symbols is what is currently being used by the modern day languages. And beyond these modern use symbols, the rest of these symbols would be simply considered as obsolete or rarely used. Hence, to conclude, 16 bits per character, because in the memory 14 bits can't be allocated. 16 bits per character would be more than sufficient for this purpose. Of course, tomorrow, if you happen to design a programming language of your own, and if you would like to support the symbols of both the modern day languages as well as the ancient languages, in that case, you can decide to allocate 32 bits in total for a character data type within your programming language. But then, since James Gosling also confirmed to this ideology that Java also would be supporting all of the symbols of the modern day languages, hence James Gosling decided in Java for a character data type, if in case you happen to declare a variable using this particular data type, then in the memory, in total, 16 bits would be allocated. But sir, if there are 16 bits that are going to be allocated, in total, how many symbols can be represented? All of you are quite sure about that particular equation. If there are 16 bits in total, 2 to the power of 16 symbols can be represented. And trust me, this is quite a big number here. 2 to the power of 16 is nothing but 65,536 symbols can be represented using the char data type in a programming language called Java. James Gosling knew this is a huge milestone considering the previous languages. 128, 256 symbols. And now that James Gosling ensured that I don't want 32 bits because my language, while it is supporting all of the languages spoken over the internet, at the same time it should also be memory efficient. 16 bits would be more than enough because I would also like to extend the support to only the symbols of modern day languages. That means in Java, using the char data type, a total of 65,536 symbols can be represented, out of which hardly less than 16,000 symbols are actually being currently used by the modern day languages. That way, Java happens to be quite a liberal programming language because it has extended the support to such huge number of symbols, 65,536. But sir, we also realize the fact here that in the Unicode standard, there are a total of 1,49,813 symbols. Out of those many symbols, how is it possible to exactly utilize 65,536 symbols? That is when you have to be introduced to two different encoding formats of the Unicode standard. The first one is technically called as UCS, Universal Coded Character Set, and the second one is technically known as UTF, Unicode Transformation Format. And between these two encoding formats of Unicode, the second one, which is UTF, Unicode Transformation Format, happens to be the quite popular one. And further, in the UTF encoding format, there are three different variants. There are three different encoding schemes. The first one happens to be UTF-8. Next, it is UTF-16. Here the number indicates the length of the binary code. And finally, there is UTF-32. And also, there is something important that you should be knowing about each of these UTF encoding schemes. UTF-8 happens to be a variable length character encoding. That means it is not fixed. In case of UTF-8, either 1 byte, 2 bytes, or 3 bytes, or 4 bytes can be allocated. Similarly, UTF-16 also happens to be a variable length character encoding. Either one set of 16 bits, that means 2 bytes, or two sets of 16 bits, that is 4 bytes, would be allocated under UTF-16. But when it comes to UTF-32, it is not a variable length character encoding. It is a fixed length character encoding scheme where always exactly 32 bits, nothing but 4 bytes would be allocated. And out of all of these three UTF encoding schemes, since Java wants to use exactly 16 bits for the character data type, it abides by the UTF-16 encoding scheme. But sir, just now you had mentioned that in UTF-16, either 2 bytes or 4 bytes can be allocated. Java follows a single sequence of UTF-16 encoding format. Great. With this, we are good to conclude our entire discussion on the character encoding formats, namely ASCII and Unicode. But before we conclude, there are few pointers with respect to char data type that I would like to reinforce and solidify our understanding. Starting with, what is the format followed by the char data type in Java? We know it is not ASCII anymore, 100% it is going to be Unicode. And Unicode also, we know it is going to be a single sequence of UTF-16 encoding scheme. Next, what about the size of char data type in Java? In C language, it was 8 bits, 1 byte. But in Java, definitely it is going to be 16 bits, nothing but 2 bytes. And in total, how many symbols can be represented? Is it 128 or 256? Neither. In Java, we can represent a total of 65,536 symbols. And what about the range, sir? Once you start assigning the Unicode values in terms of their decimal Unicode values, the range happens to be 0 to 65,535. In total, 65,536 symbols. We are eternally grateful for all the knowledge that you have provided to us with respect to these character encoding formats, Zabi sir. At the same time, we are very curious to see the Unicode table. We want to see what those 65,536 symbols are. And we would also like to confirm whether the symbols of our native languages are included in the Unicode table or not. Right. This happens to be the official Unicode table. I hope all of you are able to notice that I'm referring to the latest version of the Unicode standard, which happens to be 15.1. And now, if I happen to scroll down a little bit, what you're already able to notice here are the names of the different scripts supported by the Unicode standard. I don't know how many of my learners are aware of this fact that the Hindi language itself has been derived from a script called as the Devanagari script. That means in these Unicode charts, you will not be able to find the name of the language. Instead, what you will be able to find here is the name of the original script from which the language was derived. Hence, now if I would start looking out for a script called as the Devanagari script, I realize that this is where it is. And the moment I click on this, I should now be able to see all of the symbols of the Devanagari script supported by the Unicode standard. Congratulations, these are nothing but our Hindi language symbols. And I'm already able to notice those big smiles on all of my learners' faces here. But sir, Unicode happens to be a character encoding format whose job is to assign a Unicode value to all of these Unicode symbols in the binary format. Where are those binary sequences? Please understand, I had clarified this previously as well, that we human beings are not at all comfortable whenever we have to deal with numbers in the binary format. We will not be able to make sense out of it instantly. That is the reason why the developers of this website have decided to express those Unicode values for all of these Unicode symbols in the hexadecimal format. And where are those hexadecimal values, sir? Right below the symbol. For example, if I would like to know what is the Unicode value of the very first alphabet of the Hindi language, which happens to be A, all that I have to do is just look below the symbol. It is nothing but 0905. Similarly, the Unicode value of the next A, the second letter of the Hindi language, happens to be 0906. And for E, it happens to be 0907, and the list goes on. Anyways, let us get back to the Unicode charts. I hope all of you are able to notice in this list, there are different scripts here. Bengali, Assamese, next we have the Gujarati, next we have Gurmukhi, and here we have the Kannada script, here we have the Malayalam script, next we have the Oriya script, here we have the Tamil script, here we have the Telugu script. Let us do one thing, let us get back to the Kannada script and try to explore the symbols of the Kannada language. These are nothing but the symbols of the Kannada language. And here if I have to figure out what is the Unicode value of the very first alphabet of the Kannada language, which is nothing but this A. As you can notice, it is nothing but 0C85. And I'm sure all of you are aware of this fact about the hexadecimal format, that after the number 9, it is going to be followed with letters indicating the hexadecimal digits. Hence, it is a proof that all of these Unicode values are in the hexadecimal format. Anyways, let us once again get back to the Unicode charts and try to explore some other language here. Maybe this time it would be this Arabic script. And as you can notice, all of these are nothing but the Arabic symbols. Not just the symbols of the spoken languages. You will be shocked to notice here, there are symbols which you would call it as emojis. Those emojis that you have been frequently using it during your WhatsApp conversations are also nothing but characters in the Unicode format. Anyways, I hope with this discussion, all of you have also been able to understand as to how to explore these Unicode symbols and how to find their corresponding Unicode values in the hexadecimal format. And after understanding all of this, I am sure that all of you are currently experiencing a feeling like this. Anyways, let us keep aside our feelings for time being and let us immediately get back to the Unicode charts. Though we have seen the symbols of all of the other languages, but then how about the symbols of the English language? As we all know, the English language has been derived from a script called as the Latin script. All that I need to find here is a script called as Basic Latin, and this is where it is. And the moment I click on this, I should definitely be able to see all of the symbols of the English language. And there is one crucial point with respect to the Unicode character encoding format that I would like to emphasize here, which is the Unicode format has ensured 100% backward compatibility with the ASCII format. What it means is all of the first 128 symbols of the ASCII format. In fact, not just the 128 symbols, the 256 symbols of the ASCII extension containing the Latin English symbols have been inherited as it is into the Unicode character set. Ideally, what it means is, in the ASCII format, if for the capital letter A, the ASCII value happens to be 65, then for the same character in the Unicode format also, the Unicode value happens to be 65. Similarly, for the lowercase alphabet a, both in ASCII as well as in Unicode, the value happens to be 97. But sir, the value that we are able to see here happens to be 0061. Please understand, this is in the hexadecimal form. If you happen to convert this Unicode value from hexadecimal to decimal, take it in writing from me, 100% it would be 97, ensuring backward compatibility with the ASCII format. Now, let us proceed and do this quick exercise of assigning the binary sequences to all of the 65,536 symbols of the Unicode character set. I am sure all of my learners are able to recall that we had done the same activity for those 128 symbols of the ASCII format. Now we have to do the same for the Unicode character set symbols. Let us consider all of these to be the symbols of the Unicode character set. I am damn sure there is a certain first symbol in the Unicode table which unfortunately I am not aware of it. Hence, I would simply represent it as first symbol like this. Certainly, there should be the second symbol. We do have the third symbol, and somewhere in between, I am 100% sure we have the uppercase English alphabets like this. And somewhere down the line, we do also have the lowercase English alphabets. And like I had mentioned, that Unicode encoding format is not biased only towards the English language. That means it would also be including the symbols of all of the other commonly spoken languages. That means definitely we should be able to find the symbols of the Hindi language. We should also be able to find the symbols of the Kannada language. Anyways, the last but one symbol, I have called it as penultimate symbol, and the last symbol I would call it as the ultimate symbol. Now let us quickly assign the binary sequences to each of these 65,536 symbols. What would be the binary code for the very first symbol, sir? All of you know the character data type in Java, in the memory, it would be occupying 16 bits. Hence, for the very first symbol, it is common sense, it would simply be 16 zeros like this. But sir, in the Unicode chart, we have just now been able to see they had not mentioned the binary code. They had mentioned the Unicode values in the hexadecimal form. Is it possible to express these binary values in the hexadecimal format as well? 100% yes. And how to do it, sir? Just remember this trick here, which is whenever you would want to convert a binary number to hexadecimal, in the binary number, you have to start grouping four binary digits together. And for every single set of 4 binary digits, it would correspond to 1 digit in the hexadecimal number system. That means 4 zeros in binary, it is nothing but 1 zero in hexadecimal. Since we have got 16 zeros here, it would be nothing but 4 zeros in hexadecimal. And since this value is in the hexadecimal number system, that is what the letter H would indicate. Similarly, is it possible to express it in the decimal number system, sir? 100% yes. All of us in our schooling itself, we have learned how to convert a number between different number systems. And the same number in the decimal format, it is nothing but 0. And both of these Unicode values, which are not in the binary form, all of you know what it is called as, nothing but code points. Let us proceed to the second symbol now. You know how the binary code would be changing the sequence. It is from the right, you just have to change the binary digits. This would be the binary code for the second symbol. And its corresponding hexadecimal value would be this. And the decimal value would simply be 1. Similarly, this would be for the third symbol. And what about the character A, sir? We know both in the ASCII format as well as in the Unicode format, its value happens to be 65. 65 in decimal, it is nothing but 0041 in hexadecimal. Just now all of you have seen it in the Unicode chart. But then, how would we be able to convert it into binary, sir? Trust me, the binary equivalent also happens to be the same, just the way it was in the ASCII format. The only difference is, in the ASCII format, it had only these 8 binary digits. But since in the Unicode, it happens to be a 16-bit binary code, the remaining 8 bits are simply going to be padded with zeros. But sir, how did we derive this binary value, sir? If you have got to know the decimal value or the hexadecimal value, converting it into the binary form is a cakewalk. For example, if you would like to convert the decimal number 65 into the corresponding binary value, you know it is just the base 2 format that you need to apply. Simply start dividing that number by 2. Anyways, I'm sure all of you know how to do it. Let us proceed to the next symbol, which happens to be B. Its decimal value would be 66. This would be the hexadecimal value, and the corresponding binary value would be this. Same would be the case with respect to the next alphabet, which happens to be C. Now moving on to the lowercase alphabets here. For the small letter A, you know both in ASCII as well as in Unicode, the value happens to be 97. And the corresponding values in hexadecimal and how the binary values can also be extracted, I'm sure all of you know how to do it. Anyways, let us move on to the non-English based symbols. For example, how about this Hindi language symbol, which is nothing but A? All of you know its hexadecimal value happens to be 0905H. Now, how do we convert it into the binary equivalent, sir? Let me explain. I had already explained this during our discussion on prefixes associated with integer literals as to how do we convert a number in hexadecimal to its corresponding binary equivalent. There I had conveyed to you that every single digit in the hexadecimal number should be expressed as a 4-bit binary code. That means, to start with, we have a 0 in the hexadecimal number. 0 in hexadecimal, it is nothing but 4 zeros in binary. That is how simple it is. Next, we have the digit 9. And how do we find its corresponding binary equivalent, sir? I am sure all of you are aware of the 8421 trick here. To get a 9, it is nothing but 8 plus 1. Hence, those two positions, I would set it with a 1 like this. And in between, I am not interested in adding either 4 or 2. Hence, I would simply place zeros. This happens to be the binary equivalent of the hexadecimal digit 9. Similarly, if you would continue to convert the rest of the digits to its corresponding binary equivalent, this is the 16-bit binary code that you will be able to extract. And now that we have got the binary value here, what would be its corresponding decimal value, sir? That also long back during the discussion on integer literals, I have already explained it. And if you follow the same process, you will get the decimal equivalent as 2309 like this. And once you have been able to figure out the Unicode values of the very first alphabet of the Hindi language, figuring out the next set of Unicode values is going to be quite easy for us, because we know the second alphabet immediately follows the first alphabet in the Unicode character set. That means for the second symbol here, the hexadecimal value would be 0906. Its corresponding binary equivalent would be this. And the same value in the decimal form would be 2310 like this. Great, sir. How about these Kannada language symbols? For the very first symbol of the Kannada language, the Unicode value in the hexadecimal form happens to be 0C85 like this. Sir, what is this letter C? I had already conveyed this. In the hexadecimal number system, after the digit 9, you don't have any other digits. What you have are the characters ranging from A to F. And this C in decimal, it is nothing but 12. And what would be its corresponding binary equivalent? Once again, apply the 8421 trick here. And if I wanted 12, it is nothing but 8 plus 4. So only those two positions have to be set with a 1. Remaining, it would simply be placed zeros like this. Anyways, if you do the entire conversion, you will realize this is the corresponding binary code. And if the same binary number, if you happen to express it in decimal, its corresponding decimal value happens to be 3205. And for the second symbol, I don't have to give any explanation. These are going to be the Unicode values. Now finally, for the ultimate symbol, what would be the Unicode value, sir? You know, since for the very first symbol, the binary code was 16 zeros. Common sense it is. For the last symbol, it would be 16 ones like this. And I had told you to find its corresponding hexadecimal value, start grouping 4 binary bits. And if you start grouping it, you will realize it is nothing but 15. And 15 in hexadecimal is represented with the letter F. Hence, it is nothing but 4 Fs like this. And the same thing in decimal would be 65,535. 0 to 65,535 means in total 65,536 symbols. Anyways, for the penultimate symbol, this would be the binary code value and the corresponding hexadecimal value as well as the decimal value. Now, it is time that we take up a real world character data and see how Java would handle that character data and how it would be stored in the memory. And I don't want to take any new piece of character data here. Since all of us are kings and queens here, let us go with the same data, Raja, that we had previously seen with respect to C programming language. This data, as of now, undoubtedly, it is in the real world form. But if it has to be stored in the memory, definitely it must be converted to its corresponding binary format. And to do the conversion, Java does not make use of ASCII. Java makes use of the Unicode format. And I believe it would be completely waste of our time if I would once again explain all of the conversions here. The only difference with respect to C language and Java would be, in case of C language, for the character type of a variable, 1 byte would be allocated. But in Java, for every single character in the memory, 2 bytes would be allocated. Except this one difference, there wouldn't be any other difference as to how this data would be stored in the memory. Because you're also aware of the fact, because of the backward compatibility, the first 256 symbols of the ASCII format and the Unicode format happens to have the same values both in the ASCII as well as in Unicode. That means if you ask me, how is the character R stored in the memory? This is how it is going to be stored. The binary value happens to be the same. The only difference this time is it is not a 8-bit binary code. This time it is a 16-bit binary code, nothing but 2 bytes. Similarly, for the next character A, this is how it is going to be stored in the memory with the only difference of 16-bit binary code. And for the remaining 2 symbols, this is how things are going to be stored in the memory for the real world character data, which happens to be Raja.